Today we're going to be talking about kinematics of uniform circular motion. What do we mean by uniform? An object in uniform circular motion is going to be moving with a constant speed. And what do we mean by circular? We mean that its path is a circular path. Imagine a car driving in a circle of radius r with a constant speed. We need to define two terms specific to circular motion before we continue. First is how long it takes the car to complete one lap. This is the period of the car's circular motion, which we measure in seconds. One revolution corresponds to one lap, one time around the circular path. The second thing we need to define is how often the car completes one revolution, or one lap. This is the frequency of the car's circular motion. One revolution per second is equal to 1 hertz, or an inverse second. Period and frequency are inversely related. If it takes the car longer to do one lap, where the period increases, it will get around the circle less often, or the frequency will decrease. The opposite is true as well. If the car gets around the circle faster, its period will decrease, and its frequency will increase. Let's take a look at the motion of this ladybug going in the circle, and we're going to time how long it takes to go around once, which will give us the period. Ready, set, go. 1001, 1002, 1003, 1004, 1005. Probably just over 5 seconds, but let's call it 5, just to make it easy. So 5 seconds to go around once means the ladybug has a period of 5 seconds. The frequency would be the inverse of that. So we do 1 over 5 seconds, so 1 divided by 5 gives us 0.2 inverse seconds, or 0.2 hertz. That means that the ladybug gets 2/10 of the way around the circle every second. What about the car's speed? To find the car's speed, the distance we're going to use is the circumference of the circle, and the time we're going to use is the period of the car's motion. This linear speed is tangent to the circular path. Whether you call it a tangential speed or a linear speed doesn't really matter. We can use the two terms interchangeably throughout this unit. Big question to ask is, if the car moves with a constant speed, is it accelerating? The answer is yes. Acceleration is a change in velocity. Velocity is speed in a given direction. Let's look at our ladybug friend again. This green arrow represents her velocity. So while the magnitude of it, the size of it, the speed stays constant, the direction is constantly changing. She's always facing a different direction as she goes around the circle. So because the velocity is changing, she's accelerating. So even though the speed is constant, the direction of the car is changing, so it is accelerating. When acceleration is perpendicular to velocity, that's when the direction is going to change. We call this a centripetal acceleration. It describes how quickly direction changes. The word centripetal means center-seeking. We use that term because the acceleration is always directed toward the center of the circular path. If I include the acceleration vector, you can see that as this ladybug goes around in the circle, the acceleration is always pointing towards the center of the circular path, which is why we use the term centripetal. Centripetal acceleration is equal to the linear speed squared divided by the radius. The C subscript tells us that the acceleration is along the line that runs from the center of the circle through the object. Just like linear acceleration, centripetal acceleration has units of meters per square second. Let's take a look at a practice problem solving for both linear velocity and centripetal acceleration. So in this example, we have a 5 kilogram object that's spun around in a circle of radius 1 meter with a period of 4 seconds. Part A wants to know what the velocity is. Part B wants to know what the acceleration is. To find the velocity, or really the linear speed, we're going to use the circumference divided by the period. In this case, our radius is 1 meter, so our circumference is 2 pi times 1, and our period is 4 seconds. So if 2 pi times 1 divided by 4 gives us a linear speed of 1.6 meters per second. In part B, we're trying to find the centripetal acceleration. So we use AC equals v squared over r. that v is going to be the 1.6 that we found in part A. So we have 1.6 meters per square, 1.6 meters per second squared over 1 meter. 1.6 squared is 2.56 divided by 1, gives us a centripetal acceleration of 2.6 meters per square second.